Hello, good morning and welcome to our second live webinar, Plasma in the Dental Lab and Implantology. My name is Simona Lerach. I'm the head of sales and marketing from Reliant Plasma, and together with my great team here today, Andrea Wertmann behind the camera and Florian Freund, our plasma specialist and head of the R&D department, we will show you in which special application fields in the laboratory cold plasma can be used, and which great results for the patient in the end can be affected by the use of cold plasma. So I hope you're very excited like me, and now I want to introduce you our reference. Starting with the first part of the webinar is the cold plasma in dental technology. And our colleague Moja Taschbayatze from the University Medical Center Mainz will describe the introduction of cold plasma in dentistry. We know that there are many studies for the sterilization, for the good effects of plasma wound healing, and he will show you, based on in vitro studies, the great effects of the plasma activated materials. Followed from the next lecture, Dr. Sebastian Schaubach from the company Hydrophilic Instruments, we will have a look on very difficult treated structures in the medical field, especially in the dental implants, and he will show us how to use the special Picoliter systems can be used for the activation of dental implants and how it can be measured by this technique. And also he will give us a first insight about the imaginary contact angle measurement, and he will show us how very difficult structures also can be measured. And it's very exciting for me, and I hope for you too. And the last part is referred by my colleague Florian Freund. He's our head of sales from R&D, and he will present our latest product innovation, the ImplantWrap concept. In this concept, we want to show you how materials, dental implants, can be activated by our concept, and he will show us the latest in vitro studies to this topic. At least we will start together with you and our experts a Q&A session to have an external exchange, and maybe you have some ideas where you can use the cold plasma in your company. Before we get started, we have some guidelines during the webinar. This webinar is being recorded and will be made available to you so that you can share it with others and watch it again. All participants are muted during the webinar. But if you have questions, please use your chat panel in the control system and ask. All questions can be answered after the webinar part or after in the Q&A session. Now I want to give you a short overview of our company history. In 2002, Reliant Plasma was founded as Brandhausen Plasma GmbH by Maschinenfabrik Brandhausen. Our goal was to create innovative cold atmospheric plasma systems for the industrial market. Already in 2009, we were able to launch our first portable product line, Piezo brush. 2010 and 2011, we won very innovative awards for the development in cold atmospheric plasma solutions. In 2014, the management team, Dr. Stefan Montesheim and Klaus Forster, become 100% shareholders. In 2015, we passed the regulation for the ISO 9001, which enables us to get in touch with the automotive players in Germany. Since 2018, we became a member of the TDK. And already in May 2020, we launched our latest Piezo brush handheld device line. She's very intelligent and usable for many different application cases in the dental laboratory, by the dentist chair side, and in the dental stationary field. Last but not least, we received last year and get it this year, our certification for the ISO 13485, that we are certified like the medical regulation devices and are able to produce medical devices together with strong partners in that field. Now, I'd like to hand over to my colleague, Mr. Moya Tashbayadze, and see you soon.
Hi, can you hear me now? Hello?
Now we just need the camera.
So, hi. Hello, my name is Martas Bayatze, and I am a dentist at the Department of Prosthetic Dentistry at the University of Mainz. And I'm glad to present you today about the cold atmospheric plasma in the dentistry. So, wait a minute. So, we're going to talk about the cold atmospheric plasma in several dentistry fields, and after that we're going to talk about our own study with a Piezo brush 3. So let's get started. There are several ways for plasma generation. Pressure and temperature are important factors in the main categorization of the plasma sources, but we're going to stick today and by the cold atmospheric plasma, which is here. And the cold atmospheric plasma aroused interest in many fields, probably because of its temperature and pressure. Those two factors make it possible to apply the generated plasma on surfaces without changing the bulk or damaging the bulk. And it can be also used on vital tissues. If you take a look through the studies about cold atmospheric plasma and dentistry, you will realize it can be used almost everywhere. And here are some main fields: the modification of dental implants, the surface decontamination and sterilization, and last but not least, enhancing adhesive bonding. So we'll start with the modification of dental implants. Ting et al. Investigated in a vivo and vitro study the biofilm decontamination and cell addition on titanium implant surfaces after a cold plasma treatment with Piezo brush 2. The results are very promising, and due to the plasma treatment, the hydrophilic has been increased, and as a result, the cell addition cells as like osteoblasts or bone cells is also increased, which leads to an improvement in the osteogenic activity. You can see this effect histologically here. And if you compare the untreated implant with the treated implant, this is here the implant and this is here the bone, you can see that the new bone building around the treated implant is significantly higher compared to the untreated implant. They also demonstrated the decontamination ability of cold atmospheric plasma on titanium samples. The samples were contaminated with Staphylococcus aureus to develop a biofilm culture. And after the exposure of plasma, a significant reduction was noticed without damaging the morphology of the surface. So this decontamination effect can also be a therapeutic supplement in peri-implantitis. which lead us to the second field, surface decontamination and sterilization. All three fields, periimplantitis, periodontitis, and endodontics, it's all about elimination of the inflammation or decontamination. So the cold atmospheric plasma has promising potential to be used as a supporting method to heal those diseases. And cold atmospheric plasma can be also used in the disinfection and sterilization of dental instruments. A company in Netherlands installed cold atmospheric plasma in their sterilization device, but I forgot the name of the company. Maybe Ms. Little can tell us this after the webinar. And now we get to talk about enhancing the adhesive bonding. Well, adhesive bonding is widely used in the dentistry. Several treatments depend on this technology. It's possible to prepare defect-oriented, which leads to maintain healthy tooth structure, which enables minimal invasive treatments. But in order to get a long-term stable attachment, the surfaces must be pre-treated, and it depends on the composition and the properties of the materials how to pre-treat them. Sandblasting and hydrofluoric acid are main pre-treatment options, but unfortunately with a couple of disadvantages. For example, sandblasting can cause micro cracks in the restoration, which can affect the stability of the restoration. Hydrofluoric acid is a very dangerous acid, and we would be very happy when we doesn't have to use it anymore. So an alternative, as you can see, an alternative method is to improve that adhesive bonding is very desirable. And because of this, previous studies from Nelson et al. Investigated possible methods to improve this adhesive bonding. They used plasma, cold atmospheric plasma, to increase the surface energy and the wettability. They have also reported that an increase in the tensile bond strength on the zirconia surfaces is also achieved, but unfortunately they used argon and oxygen as operating gases, which leads us to our study. We already know that plasma pretreatment increases the wettability on titanium and zirconia, but other dental materials have not been investigated yet. The influence of cold atmospheric plasma with ambient air as operating gas is also not enough investigated. Therefore, we decided to do our own study and answer a couple of these questions. Does cold atmospheric plasma with ambient air influence the wettability of the surface of dental materials? How long do we have to activate or treat the surface with plasma to get a sufficient wettability? Does the distance of the treatment play a role? And most important, the question is, does cold atmospheric plasma improve the bonding strength? In order to answer the questions, we organized our study in 3 steps. First step, surfaces preparation. The second step is quantification, and the last step, addition. So we start with the first step, which is surfaces or materials preparation. We've chosen titanium, hybrid ceramic, lithium disilicate, and zirconia as samples. And as you can see, we have we polished the titanium samples so we can get rid of the scratches and the unevenness on the surface, and so we can get an equal surface roughness. The ceramic samples were digitally designed in a cube shape and milled. After the milling, they were centered as recommended from the manufacturer, and at the end they were polished to 800 grit to get an identical surface roughness. And now we have got our samples ready, and we're ready for the next step, which is the evaluation of the wettability. We did this in a cooperation with Max Planck Institute in Mainz. But before we get to that, would like to explain a little bit about the wettability and how to interpret it. If you take a look at this liquid drop on this solid surface here, you will see, and compare this liquid drop with this one and this one here also, you will see that those two are flatter, and which means that the surface here is hydrophilic and here is less hydrophilic, and the liquid drop makes an angle to the solid surface. And you can interpret this as the lower the contact angle, the higher the wettability. Indirectly, you can say the higher the surface energy also. So we have got now our samples, and now we can do our measurements on this device. It's a goniometer. Here you can see the camera. Here you can see the light, and this is our syringe. This is the platform where the samples are placed. And our syringe was a 0.1 milliliter syringe, a drop of water of 3 microliter in a speed of 1 microliter per second. Our plasma device was attached to an holder to keep an equal distance between the samples and the plasma device. We've chosen a distance between a plasma device and titanium of 0.5 millimeter and 2 millimeters between the device and the ceramic samples. Here we can see an example of a water drop on the untreated and treated titanium sample. And as you can see here, the water drop here with a much higher contact angle to the surface. And here, after treating it with plasma, the water drop has spread it. But you can see this on this video much better. Here is an untreated titanium sample. And here you can see how the reaction is after treating the sample with 30 seconds. The water spreads directly. So now we got our results. We have done 15 measurements per time unit, and we've measured the plasma effect after 5, 10, and 30 seconds. And as you can see, after 5 seconds, we have a significant reduction of the contact angle, and with further plasma activation, we have a reduce on the contact angle, not that much, but it's also a result. On the zirconia surfaces, you can see that after 5 seconds, we have also significant reduction in the contact angle, but with further and longer plasma treatment, you can see that there is no significant reduction or difference. Lithium disilicate shows also good wettability after plasma treatment. And after 10 seconds, there is no significant difference anymore. Hybrid ceramic is almost the same as zirconia. After 5 seconds, we have a significant reduce on the contact angle, and with longer plasma treatment, there is no significant reduction or difference. So our conclusion is that the hydrophilicity of the surfaces increases with further plasma treatment, not on all of the samples, especially on zirconia and hybrid ceramic, not. But what we can see and interpret that after 5 seconds, we have a high reduction of the contact angle, and 5 seconds seems to be a sufficient treatment time to get a good wettability on the surfaces. But we still have questions, and why don't we have a complete wetting, and does the humidity affect our experiment? Those questions we're going to answer in further studies. We're working on it. And now we can get to our third step, which is adhesive bonding. We are working on this too. My colleague Caroline Gergen is doing the experiment, I think, right now. And in a couple of weeks, we're going to show some results about the strength, bonding strength of we achieve improvement in the adhesive bonding. But here is an example of how it's gonna be when you use plasma to treat your restoration before you bond them. Here is a patient with 2 zirconia implants. We placed the scan bodies and scanned them in order to mill and design and produce the crowns. Those are the crowns, and this is the so-called abutment, which gets into the implant. And in order to attach the crown to the implant, you have to bond this abutment into the crown. And here's a setup how you do it. This is our rising cement, the primer, and of course the plasma device. We've activated the surface or treated the surface with the plasma device, which was not a very complicated way. It was really easy and easy to use. So is this the future we can rely on? Many in vitro studies reported about potential clinical use in several fields, as like implantation and peri-implantitis therapy, also periodontal and endodontic therapy, and of course as a supplement to enhance adhesive bonding. But more in vivo studies are required to begin with the clinical use. And of course, appropriate devices for oral use should be developed. And thank you for your attention, and special thanks to my colleagues at my department, Dr. Stefan Benterschek, Ms. Caroline Gergen, and Ms. Manuela Merais. And a special thanks to Professor Doris Vollmer and Ms. Katharina Hegner at the Max Planck Institute. So,
there are 2 questions right now. The first one is, what's the durability of a plasma treated surface? does the hydrophobic recovery have any role here?
Excuse me?
So what's the durability of the plasma treatment? Does the hydrophobic recovery play any role here?
The hydrophobic recovery is noticed after 1 day, actually. But if you treat your crowns or restorations immediately before you bond them, so you don't have to worry about that.
Okay, so hello, my name is Florian Freund. I just also want to answer to this question. As Mr. Bayatze already told you, though, you can recognize a reduction in the hydrophility at 1 day, for instance. As we have shown in our last webinar, the main reason for the increased hydrophility is the reduction of carbon and other adsorbates on the surface. So it depends on your environment how fast the recovery is. But as Mr. Bayatze also answered, typically you're using it directly at your site in advance of the application. But so far we also could measure still increasement of the contact angle 1 day after the treatment, but it depends on your environment. So if you have your hydrophilic surface, there are also this higher surface energy, so adsorbates are likely to stay on the surface. So you have an exponential decay of the surface hydrophility. But you can still measure the effect 1 day after treatment, but then it's mostly gone.
And do you have any experience on the treatment of zirconia and how long it lasts on this material?
Treatments on zirconia.
Yeah.
With plasma.
Does the last longer or?
If it lasts longer, also 20 hours. As I could see, I did an experiment on this that I treated the zirconia surfaces, and 24 hours later I checked the contact angles and the wetchability, and they have recovered. It's between I would say a couple of hours, but how long exactly, I can't tell you this right now.
Okay, thank you very much. So the effect on zirconia is quite the same. The surface recovery effects are also the same. So the timing behavior of the recovery is quite similar. So this is what we also have checked in our experiments.
And one last question, is there any incidence of plasma cytotoxicity?
Excuse me?
Have you done some toxicity experiments on that?
No.
Okay, so I will demonstrate an answer to this question later, but so far we have very new results from our research partner, Professor Dr. Smith at the UKE in Hamburg, and we have a clear sign that there is no toxicity on the surfaces after plasma treatment. So we are still just very new results from cell attachment studies which demonstrate no toxicity on the surface.
That's it for the moment.
So we will see later. Bye.
Thank you, Mr. Bayatze, for the very impressive presentation of your latest results. And this is a feeling for us that we are on the right way to create and develop new products for this market, because it requests the market. And I hope that we will find good partners which we can develop in our team, and that we are able to make a decision what is really needed for the dentistry market and for the dental labs, and what can help the dentist chair side for his daily work. So I want to hand over now to our next lecturer, Mr. Dr. Sebastian Schaubach, and he will take over the scene with the containment management. Have a nice.
Okay, hello to all of you. I hope you can see and also hear me. So same question like for the presentation before. Can you see me, the guy, or can you see now the presentation?
Both. It's perfect now.
Okay, perfect, perfect. So then let me quickly switch the screen and then maximize here, and then we can get started. Okay, so now welcome to all of you. Today I want to show you a little study from our side that we did on very challenging surfaces and how you can study the effects of a plasma on these surfaces. So we are data physics instrument and we are a manufacturer for equipment in order to analyze surfaces and interfaces. First of all, we were already founded more than 20 years ago and do this since quite a while. We are located in Germany, in the south of Germany, close to Stuttgart in Filderstadt. And there we have around 30 people of staff at the moment. So a lot of them, they are the chemists like me, for example, or the physicists or the engineers. And together we develop some really nice machines that we are shipping out to over 70 countries and have quite a good product portfolio, I would say, for several different applications. Our machines you can basically find in any industry you can imagine or in any research lab you can imagine, because surface and interface science, it does not matter whether you develop paper or whether you are in the oil industry. You always want to know how different substances will interact with each other when they come into contact. So our devices are everywhere basically. Okay, and to just pick out a couple of the customers that are using our equipment, the NASA uses them in order to develop nice coatings for the spaceships. The Bank of Thailand uses our equipment in order to make the banknotes and the printing on the banknotes false-proof. And also chemical companies like BASF, for example, use it in order to determine surface tensions of new formulations, or Intel in order to glue on electronic boards or analyze the chip surface to see how it can be modified. So the equipment that can do this kind of measurements is on one hand our OCA. So this is an optical contour analysis system. You have a camera system here. You have here a mobile sample stage, and then with this kind of dosing system on your sample that you see here in the center, we are placing a drop of liquid, and with the camera system, we analyze the contact angle. And if you do this with a couple of different liquids that water, diiodomethane, ethylene glycol, then you can calculate a surface free energy, and this is giving you an information about the polarity of your surface. We also manufacture force tensiometers like the DCAT that you see here on the other side. And with this instrument, you can determine surface tension, critical Meissner concentration, or adhesive forces. So left side is an optical method to study interfaces and surfaces. Right side is a force-based method. In addition, we also have stability analysis systems or spinning drop tensiometers to measure very low interface tensions. And we have the humidifiers to control the humidity very precisely in a sample chamber. Okay, I don't want to go too much into details for our other products, but what I want to talk with you today is about implants. So just imagine your body has turned weak in some spot. It can be the joint here in the leg or here in the knee, for example, or your blood pipes are jammed. So when you have this problem, now most of it can be solved quite easily. So you will get a new implant into your body. But it's not so easy like we think, because the implant, it needs to be accepted well by the body. And our body does not know metals. So the metal surface, it needs to be coated in a way or treated in a way to make it compatible with the body. Because our goal is that there is a good contact between the implant surface and the tissue in your body. And in order to get a good contact, to keep it simple, normally we say the surface free energy of the material should be very high, and the contact angle of water on the surface of the material should be very low. So this means if you try to improve the surface properties of, for example, a tooth implant, you want to treat it with plasma to make the surface more polar, then of course the surface free energy will go up. This is good for getting the tissue accepted on the material. If you treat a surface with plasma, then the surface becomes more polar. So this means the contact angle of water is typically going down. The water is spreading on the surface. This is also a positive effect. So this basically means plasma treating of implant material makes them more hydrophilic. Water contact angle goes down and typically more polar. So the surface free energy goes up. So this is a good way to treat implants. So let me just go a little bit more into details. When we look here, for example, at a tooth implant, you have here the screw, and this screw is put into your bone. So this is directly into contact with your body tissue. Now, it's important. We want to study the surface free energy on this implant because this can happen of the implant, higher surface free energy, better accepted typically. And it can also help us to estimate the wettability and the adhesive properties that we will get on the implant. Because also here, on this part here, you will do a gluing process. So also here, it's important that we are able to judge the surface free energy in order to find the right glue or make sure that the glue will stick nicely. Then the second parameter I had showed you, the contact angle or the dynamic contact angle, it's very important because this can give us an indication how well is the protein absorption on the implant material, and it can also give us a parameter how well is the surface of the implant wettable. Okay, so if we keep this in mind, then we go to the tool that we had from Relion Plasma and still use it now. So this one, the Piezo brush, we use it, take the implant, treat the surface, and then we can have a clear comparison before and afterwards. How does the plasma affect the surface chemistry? Because when plasma treating a surface, you know, typically you will introduce the OH groups or the oxygen groups on the surface. So you are increasing the polarity. And this we can measure very, very easily with a contact angle measurement or with a surface free energy analysis. But it sounds easy, and if you think about big samples, it's very easy to place a drop of water on it and measure the contact angle. But we want to talk now about the really challenging stuff. Just imagine you have this kind of substrate. So you have here the tooth implant, and you want to measure, okay, did this surface of the tooth implant get treated homogeneously with plasma? You know, the lightning is always striking the highest point. So does this mean for us, okay, the higher points that you see here, are they treated more for a longer time with the plasma and become more polar? Or is also the valley here, the lower part of the implants between the turnings of the screw, is this also treated well with plasma and has it changed its surface chemistry? So what we need to do is, if we want to do this and we want to know locally how homogeneous our implant has been treated, then we have to make very tiny drops, because you see it here between two turnings of the screw, we have a distance of around 700 micrometer. So we need drops that are significantly smaller than this size. I want to quickly show you this again with a simple illustration here. If we would shoot a big drop on the surface that is bridging several of the turnings of the screw, then what we would get is not the actual contact angle here in red. This is the contact angle we need to know to determine surface chemistry. What we would measure is an apparent contact angle, because we see the substrate from the side and the drop is bridging a couple of surface areas. So what we want is the red one, okay, this contact angle. And we can only get it if we make our drop so small that it can sit on a nice and smooth plane surface. If it's a little bit bent, it's no problem, but there should not be big dents and the drop should sit here on the spike, for example. So very important, if we make drops in the picoliter range, then we can analyze surface areas that are around 0.1 millimeters in dimensions. Okay, 0.1 on 0.1. Good, but how do we make this kind of very, very tiny drops? Well, we do this with a picoliter dosing system. You see the little box here. I want to show you a little close-up of this. And you can see that inside this picoliter dosing box, there is a small cartridge. So now we have taken it out. So you see this is a little plastic bottle. It has a nozzle here. And through this nozzle goes a very, very tiny pipe. Through this pipe, through under pressure with a normal pipette, you can suck in your testing liquid. then it's inside the cartridge, and on top is still a little bit of air. Then now you insert it into this holder, and the holder, the Picoliter dosing system, is generating an ultrasound pulse. You can imagine it just like a noise, butts, butts, butts. And when this noise is generated, then of course the remaining air up here, it's compressed. And from this compression and relaxation, then a tiny drop is shooting out of the nozzle. So we can dose down liquids with the viscosity is not too high, of around 30 picoliters. And we can do it at a very high rate, 1000 drops per second. So for our dentist application, this is not so important, but the small drops, they are very, very important. Of course, to see these very tiny drops, we need to have a microscopic optics. So this is really small substrates already. So you see this microscopic optics, and it's really nice. Normally, you know, microscope, you have to go with the objective super close to your substrate. But for this setup, it's not needed. We have here a good working distance, 9 centimeter. And even with 9 centimeter distance, you can analyze the substrate very, very well and have a very, very high magnification. Okay, then I want to show you one video how this kind of system is working. So maybe you know we make also the normal contact angle analyzer machines with syringes. So now I show you a video with this kind of special picoliter dosing system. And I show you how with an automatization, we target 14 positions on our substrate. So you make a little automatization program inside the software, and then automatically you can let the drops be dispensed. So you see on these areas where the drop shoots, we measure. So you saw here a piece of dust as a size comparison. We left it inside the picture. And you can see it very nicely here. So now 14 areas we have measured. And then what the software will do, it will evaluate it. It will take a fitting function to determine here the contact angle of this drop. So you see it here, 14 position we had targeted, and the average contact angle is around 25.7. The accuracy is plus minus 1 degree, so this is actually very, very good for this kind of very, very tiny drops. Okay, so this means for us, no matter even if the surface is very small, if you have a stent here, for example, or a tooth implant, we can target the surface and place tiny drops on the surface and also analyze them. Now, what does this have to do with the plasma? I want to show you one little application we recently did. So we took one tooth implant, you see it here, fixed it on the sample table with a bit of this. This is like the mask the kids like to play with, this Knete, we call it in German, the English word I don't know. So we stick the implant inside, bring it in close proximity to the dosing system, and then we shoot tiny drops onto the surface. And now you see here on the left side the results. So implant number 1, we have a look at it first. We took it out of the package in its original state. Then we put a drop of water, diodomethane, and some other liquids on it, and the software is calculating for us the polarity of the surface. This is the so-called surface free energy. Now you have in blue the dispersed part for non-polar interactions, and you have in red the polar part from polar interactions. So if the surface has polar groups or OH groups or ketone groups, then this red part, it will be big. So now have a look at the beginning. When we take out the fresh implant, the implant surface is mainly dispersive, only a little bit of polarity. Now we take exactly the same implant and we do a plasma treatment with the Piezo brush. And then you can see, wow, now all of a sudden the polarity of the surface is increasing very, very much. And this is then later on the effect you will see in your dentistry lab, because now the surface is very polar, and now polar liquids like water, they like this kind of surfaces. They will spread there very easily on the surface and will lead to a good coloring process if it's a water-based color and you want to color, for example, the ceramics that you put on the tooth, or you will have a very good wetting if this tooth implant is later on screwed in your body. So the cells, they like this if the polarity of the surface is high. So you can measure this indeed. So this morning when we did it in German, the webinar, I saw how the colleagues, they paint the tooth and they qualitatively have a look at it. Okay, how is the drop spreading on the surface? Well, with these values here, you can understand why it's spreading. Before the treatment, you have little drops on the surface, and after treating, it can spread and bind very well to the surface. This is all about the surface chemistry, the surface polarity. Now we have a look at another implant, implant number 2. You can also see after the treatment with plasma, the polarity is going up. You even see ceramic implants. Of course, they also have some coating, the ceramic implants. And after you treat them with plasma, you can also see polarity goes up very much. So we can check here very locally, no matter whether you want to know it on the higher point of the screws or in the valley in between, you can locally check how the plasma treatment is influencing the polarity, okay? Good, so very challenging substrate, small surface, but we can measure it. It's no big issue for this kind of dosing system. But then there is another challenge. So I told you that in fact, the surfaces that they get accepted well inside your body, they should be as hydrophilic as possible. Okay, the contact angle of water should be as small as possible. So what does this mean? Okay, a surface like the one in the middle where you have a 90-degree water contact angle, this is not ideal for an implant. A surface like here where the water is spreading completely over the surface, this is very, very good, but it's difficult to measure on the surface. So the reason is, if you have the total spreading here, you cannot measure it optically, because for optical measurement, you need to have a static drop that spreads maybe at the beginning, but then it reaches an equilibrium point where you can measure the contact angle. But for total wetting processes, you go towards a contact angle of 0. So your drop is becoming bigger, and then wets the whole surface. So in this case, we need a different piece of equipment. We do this with a force-based method, this analysis, with a tensiometer. So with this method, optical method, it would give you for all substrates maybe a contact angle of 0, complete spreading. But with the force-based method, we can distinguish between different superhydrophilic coatings. And this is very important. So for you in development, if you develop coatings for implants, for example, you would not be happy if you have made 10 different coatings, all of them give you a contact angle of 0, and then which one was the best. So this is not nice. But if you do imaginary contact angle analysis by tensiometer, then you can distinguish these, okay? And I want to explain to you a little bit why. So maybe first, so that you really understand it, why we cannot do it optically, you drop a drop on a surface, and even if you have a high-speed video system, the drop is spreading, as you can see, and it never reaches an equilibrium state. It's always becoming bigger, so contact angle would go towards 0. Okay, but now how do we measure this kind of substrates? Well, you do it with a tensiometer. So you see one here. Tensiometer is a force-based method. So in the head of the tensiometer, you have a balance, a very fine balance. Then you have here a sample holder for your probe. So the implant, it would be this yellow body here, okay? So implant, put to a holder, then move it gently into a liquid and measure the force that can be detected at the balance. So you see here the red liquid here, this is your testing liquid. Then you have here a thermostat jacket, because these processes, they are very often highly temperature sensitive. And in addition, you have here a mobile sample stage. So the measurement is completely automatic. You do not need to move the stage up and down or anything. It's too sensitive. Better step away from the table and let the machine do everything. Okay, then let me go and explain a little bit, at least, the physics behind this. So in order to determine the dynamic contact angle, the dynamic wettability with a tensiometer, we use the Wilhelmi method. Most of you know a tensiometer maybe to determine the surface tension of a liquid. Now we do it the other way around. We use a known liquid, for example, water, and then we place an unknown sample into this liquid and characterize this solid sample. How to do this? The yellow one is our solid sample. We dip it into the water and then we pull it out again. And when you pull it out, you get here the so-called receding contact angle. When you dip it in, you get the advancing contact angle. For us, mainly the advancing contact angle is interesting for the plasma treatment, because this determines how fast the water spreads on the surface. The receding one is how fast it de-wets the surface. Okay, now what kind of forces does our balance detect? So the balance is, of course, detecting the weight of this lamella here. So you can have a look here. And the weight of the lamella, it depends on the size of your substrate. We call it L, wetted length, 2 times A, 2 times B. It depends, of course, on the contact angle that we have here on the surface, and it depends on the surface tension of the liquid. But we use a known testing liquid. We can measure the dimensions of our plate. So the only unknown here is the contact angle that can be very easily determined. But we have a little problem, because when you look here now, sample is a bit underwater. So this means there's also a buoyancy effect. So we have to do the measurement in a way that we can exclude this buoyancy effect. And it's actually quite simple how we do this. So the program is running. It's dipping your sample into the liquid. We have here the immersion depth. Afterwards, it's pulling the sample out again. And then, in order to exclude the buoyancy term, we need to just extrapolate. Look what we are doing. We are extrapolating the pulling and also the pushing to zero immersion. So when the end of your substrate has reached the surface of the liquid, this is when we determine the contact angle. And then the term is simplifying, and you can see here the contact angle as a measure for the wettability is equal to the mass of the lamella that we detect, gravity constant, the size of the sample, and the surface tension. And now we are in the game. But now the problem is cosinus, it can normally only be a maximum of 1. But what do you do if some effects render this term here on the right side higher than 1? So for example, you have a very rough surface, then you get some extra spreading and capillary forces. And then the force you detect here, it can be higher than 1, this term here. And then we are a little bit in trouble because of our cosine on this side. And this now is the key that we are using. So what we are doing is the following thing. With classical contact angle measurements, where your contact angle is only allowed to be a real number, there we are quite limited. So you can see force curve is going up. And now we have here a whole area where the only information we would got is contact angle is 0, finished. But this is not the whole truth, I would say, because when we expand the range of numbers that we are allowed to use to also include complex numbers, then we get also an imaginary part. And this imaginary part is rendering our scale of contact angles longer. So this means with this old method here, you could distinguish between contact angles from 90 degrees to 0 degrees. But all of these measurements here, it would all give you a number 0 as a result. But the coatings can be completely different. On one coating or on one treated substrate, water spreads very fast. On the other one, it spreads super, super fast. But for all of them, you get 0 as a result. It's very frustrating because you optimize it and you cannot see what has become better. And in order to display this very easily, we have introduced this imaginary contact angles. So this was together with Professor Jennison, who had the idea for this concept, provided it to us, and then we implemented it in our machines. So it's also called the inverse lotus effect. So lotus effect means your surface does not want to be wetted. The drop is swimming on top of the surface. And inverse lotus effect means your surface, it really very much wants to be wetted, and you get a complete spreading process on the surface. Now, very, very important, I personally think the imaginary contact angle is only one single number that can help you to classify hyperhydrophilic substrates. Some people, they also say, okay, you can just use the weight of the lamella, and if the weight of the lamella is more heavy, then it is similar to an imaginary contact angle. But just imagine you have a big sample, you have a small sample, and then the lamella on the big sample, it will always be bigger, okay? So this means if you give this information, the weight of the lamella, then you always have to also give the size of the substrate, and then it's already a bit more complicated for people to compare results. So imaginary contact angle, really very simple. The higher the I value, the more hydrophilic is your material. The scale here just continues. Very, very easy. Also here, of course, I want to give you an example where we treat some implants with plasma. Very important. This is not the same implants like in our experiment before. So these implants here, they are really super or hyperhydrophilic implants that we have chosen here. You can see implant number 1, it has an imaginary contact angle. Water spreads super fast on the surface. Also imaginary implant number 2 has an imaginary contact angle. Very important, if you would have analyzed these classically, then you would have gotten a contact angle of 0 for all these 2 implants. So they would be the same for you. You do not see any difference. But with imaginary contact angle measurement, you can clearly see, okay, this implant number 1 is much more hydrophilic than implant number 2. Now, just one little example, we also had here a third implant, and this third implant, it did not give us an imaginary contact angle at the beginning, but a very high normal contact angle. So this substrate, it was not wettable, this implant. So what we did then is we also treated its surface with plasma for a short time, 20 seconds, I think, in this case. And now you can see very clearly, wow, now the contact angle, it has become much, much smaller. So this means now it's more hydrophilic and then also more compatible to your tissue typically. So you see after short treatment time, the wettability can change completely. I want to quickly show you how it looks like when you dip a treated implant into water. So look here, this is now a holder. Up here you have to imagine the tensiometer. So this holder is put into the tensiometer. And at the end of the holder we have an implant screw. And here now is the sample vessel filled with pure water. And now pushing a button, automatically the stage will move up. I show you this one time. And you can see surface is only very, very slightly touched, but it's hyperhydrophilic, so the water is moving up through the capillary effects. So in fact, this method here for judging the surface chemistry with the imaginary contact angles, this is already used in several production facilities for implants. So they use our DCAT with this feature for quality control in order to check that all of the implants, they have really the same superhydrophilic character. Let me play it one more time. So just dip it in, water raises up. Super, very, very hydrophilic material here on the surface. So this is not just an exotic method, this is really already in several production facilities, it's used. People have their procedures, how they do it with our equipment, note it down, and then they can quantify in their quality control, this implant is good, and here is some problem with the coatings or with the treatings on the surface. Okay, so I hope this was a bit interesting to you, to also show you that really small challenging surfaces or the super hydrophilic surfaces can be analyzed quite well. So again, for the small surfaces, we have used optical contour analysis and the Picoliter dosing system, which generates super small drops and then can locally measure the hydrophilicity of a surface, and also the polarity of the surface if we do a surface free energy analysis. So this is a position resoluted method, very useful to check how homogeneous your surfaces were treated. Then another method I showed you, this is a tensiometric method, force-based method, and it can show you how hydrophilic your implant is. This is very good for quality control or also for development of new coatings, or when you just want to see the effect of plasma on your implant, how it's improving the wettability. Very important, the second method, force-based method, it's not position resoluted. So we get an average over the whole implant, so we need to be sure that the implant surface is homogeneously treated already beforehandedly. Okay, so I hope this was an interesting overview for you, for some ideas how you can do this challenging measurements. And now I would be very open for questions from your side. Thank you very much for your attention.
There are several questions. The first one is if the hyperhydrophilic implants do lose the hyperhydrophilicity if you store them some time.
Yep. This is in fact the case. So I do not know, normally these implants, they have a hypohydrophilic coating. I do not know how long this coating inside the box will keep, but we know if the implant is plasma treated, for example, the plasma treatment, it will not keep forever on the surface. So if you let it then lay around for a couple of days, so then you should, I think, go back to the initial value. So the plasma treatment is time dependent, I would say. And at least from what I know from before this morning, where one tooth doctor was explaining to us that when he opens a new bag with the implants, he is never so really sure whether the surface of the implant that he takes out is still very well wettable or whether it has already turned hydrophobic. So also this means to me that probably the coatings that are applied on this kind of surfaces, they can age. Okay, so I hope this answered your question.
Yes, thank you. The next one is, how did you determine the shape of the implants to compensate the bioions term?
Yep. So this is a super good question, because you have seen in the equation here, where I go one slide more back, then you see it better. So you see in this equation goes in the so-called wetted length. So the wetted length is just how long is the lamella around your substrate. And you can imagine for a tooth implant, it's not the same in every position, because you know the implant, it's a little bit conical. So this means the conical shape has one influence, and also it has the turnings of the screw. So this means if you go up in the position, then this wetted length will change. So in fact, if we have simple substrates, plate-shaped substrates, for example, then we will just measure the size of it and then put the size in, and then it's absolutely correct, the results. But if we have a super complex surface like a tooth implants that very often also have the gap to screw it in, then what we do is we typically measure in the area where the implant has a cylindrical shape, and then we try only to compare coatings of implants with the same shape with each other. So, you know, maybe I can show this also on one of the slides before. So there is this kind of shape for the implant, but there's also completely different shapes for the implant, like you have it here, or even with this complex piece here onto the surface. So comparing them directly with each other, the imaginary contact angle, this I would not do. I would compare implants with similar shapes. And this is actually also the procedures that the people in the quality control with the imaginary contact angles do. So they take one certain shape of an implant, then they measure the upper diameter, and then for all the implants that have this shape, they use the same value. Okay, and then the results is correct to compare them with each other. But you cannot compare the apple shape to the pear shape in this case. So this is really important. Thank you for this question.
Okay, that's it for the moment.
Perfect, thank you.
Thank you very much, Mr. Schauerbach, for the very impressive presentation of the possibility of contact angle measurement with special Picoliter dosing systems. In our daily work, we can't live without contact angle measurement to investigate difficult material surfaces. So in our first webinar this morning, we learned from our dentist that our Piezo brush handle device can be used for several applications chairside, so like fine cleaning of Gingiva formals and Gingiva cups, also for the hydrophilization of the implants, and also for the bonding, for the accepting abutments bondings. And I'm very proud that we presented today our first concept for a chair-side device by the dentist. It will be presented by my colleague, Dr. Julian Freund, and he will show you the latest in vitro studies we have made with the UKE in Hamburg and also with the OTH in Osnabrück in Germany. And I wish you a nice time.
So hello again. I'm happy to now demonstrate you what we at Reliant Plasma have already done, what we have already achieved, and what we are trying to achieve in the future with all the help of the people, as we've seen just in the webinar before me, or in the German webinar this morning. I think this is really nice to get all this information now together and see how we are developing on a very research-based case. So again, I want to just give you an overview of my presentation. I will just give a short, very short overview why surface treatment with cold atmospheric pressure plasma is good for what we are doing, how it works. For more details on that, I would really like to refer to our previous webinar, where we get in real details about technical and also on physical background on the effects. And the second part, I will demonstrate you how it is possible for you to use the technology in your daily work. So as you have seen, we have handheld device available. I will demonstrate you different modules, and I can also demonstrate you upcoming modules which will be available in the future. And last but not least, I want to demonstrate you our concept device, which is should be available to have the implant activation chair side available for much more precise and reproducible case. Again, I also want to tell you something about cases where the plasma is already used in the dentistry and in the dental lab. Therefore, also I want to refer to the webinar in the morning. As I'm not a dentist, but we had a dentist in the morning, and he really tells a lot of his daily work, and he's using his device very, very often now. And I just can refer to the German webinar to have a look at this, and probably will understand what we're currently doing in the dentist's practice and in the dental lab. So why surface treatment? I think the basic is already very well known for most of you, but with plasma treatment, we are mostly removing carbon oxidate from the surfaces and putting additionally OH groups on the surface. Dr. Schauer already presented very well. This leads to an increase of the surface energy, which can be measured in a smaller contact angle. For your work or for the dentist's work, this is better wettability. So we end, or one can say it's just an improved surface condition. The surface improvement can be used for a lot of applications in the medicine and especially in the dentist's world. This is a better compatibility, a biocompatibility. So we have got really very fresh data from our partner, Professor Smith, who is doing cell adhesion measurements and also toxicity tests that I already presented. The surface improvement, so the improvement in adhesion for bonding, coloring, and active ingredient application. I think I would also refer to the webinar we had last time, where the dental lab specialists really present what is happening with ceramics, what is happening with coloring when they have activated prosthetics, metal or ceramic ones, and how this improves the daily work. Again, Mr. Modifiers already told you that plasma has a disinfection, antimicrobial efficiency, and here the synergistic effects of reactive oxygen, nitrogen species, UV light, ions, and other plasma-specific radicals antimicrobial efficacy, and therefore leads to disinfection effect on what you're treating. I just want to remind, which we have already shown in a lot of research in advance, that the effect is a surface effect on a submicroscopic scale, which just affects the surface and does not change any of the macroscopic material properties. So I think this is just annoying now, but I will demonstrate what we here do very often with for demonstrate the effect of plasma treatment on the implants. And I can tell you again what Mr. Bayazzi already told, or Mr. Sebastian Schabach already told you that the treatment time can be really, really short to achieve such results you see here. So the increasement of the hydrophility achieves after 20 seconds of plasma application. So we've seen that the effect is still very, very impressive after 5 seconds. But as we know, there are some distortions or differences in the implant. And we also don't have a problem with 20 seconds as we have in a very flat curve. There's no over treatment possible. We say 20 seconds is really a good time for the activation of the implant. So here I want to now demonstrate the very new data we received just this week from Professor Dr. Smets, where he did the classical cell attachment and cytotoxicity studies. As I'm not a medicine or doctor, I will just refer to his speech he had in the last webinar to get details. He presented what he will do in the study. But just to summarize, we see that the plasma treatment increases the cell attachment, and we see that we don't create any toxicity on the plasma, on the implant. Sorry. Again, what is very impressive is the reference to available UV treatments of implants or titanium surfaces, which is available. So far, we know UV treatment is available at the dentist for the implant activation, but we also know that the activation time is an issue there. If you want to use the chair side, they're mostly activation times of 5 minutes, and we have activation time of 20 seconds, and we received quite similar results. So now let's come to the special part. I can demonstrate you very shortly the devices we have available and the device we are currently in development. So I think for really getting detail with the device, I would also recommend to get on our webpage. There are very good introductions to the device, unboxing videos, and also application videos. But I just want to show you how it looks like and what we know so far, how it can apply. So the device just comes in this nice box. We have the device inside, and we have the modules with the plasma generator inside. So typically, for non-R&D people, there are just 2 modules currently available, but the one is the standard module, which is for electrically non-conducting material, and our DBD nozzle, which is for conductive materials. So it depends in your daily work. If you have the activation, if you want to activate titanium implants, use the DBD nozzle. If you want to work on zirconia, ceramics, or on plastics, you can use the open module. We also know from the dental lab colleagues that they very often have hybrid materials. So then you can adjust the software in your device, and then it will also accept the hybrid materials in somehow limited power mode, should not destroy the device. So I just, for those who have never seen it before, I just want to demonstrate the open module for the ceramics. So just enter the right module. You have some software features for countdown, stop, watch, and so on. You can easily adjust the power. In the future, we will release software where you have additional features where you can control the power and the intensity independently. So with somehow pulse modulated. So then you can just press the button, the plasma ignites, and you can treat the device, the surfaces, whatever they are. Okay, so what we have seen in the video, I think from Mr. Bayatze, there has been a nice module with a very sharp needle in advance. These modules are from the predecessor device, the Piezo brush Piezo 2, but we are currently developing the same modules also for the Piezo 3. I think they will be available at the end of the year. Okay, so let me summarize the brush Piezo 2. So the Piezo brush Piezo 3 is currently available. You can buy it. It's very user-friendly, as you have a very flexible application because it's a manual process. You can activate different shapes. You can select your duration, intensity, and the power. So we know that this is very effective, and because we are already using it very long in the industrial environment, and it's safe as we have no or very moderate heat emission to the surfaces. So here's again the module near for the conductive materials, the standard module, and there's also probably a casted version of it, which may be available, for instance, for skin treatment, as it has a more moderate plasma exposure. So, but now I will demonstrate you the implant wrap concept, which is a device we developed because a lot of people, for instance, indeed people who are placing a lot of implants, say somehow are struggling. Okay, maybe it works. You demonstrate hydrophilic, but we don't know. We are setting so many implants. What's about reproducible? So maybe there are some concerns about sterility of the user, and all these concerns we take into account and try to develop the implant concept device. So here you see our demonstrator, and now we'll demonstrate how it should work. So I think the implant will be unpacked as usually, and we developed this prototype of the transfer tool, which can be attached to mainly all available implants, as it is possible to attach it to the RA shaft, for instance, which is available for nearly every implant system we know so far. Here we have a lot of different tools and implants, mostly from Camlock, which is a partner for us today. And now you have selected and taken out your implant, and you know which diameter it has. We are planning to have 3 sterile reactor sizes available to can activate all available implant diameters. So this is a medium-sized reactor for a medium-sized implant. This reactor acts as a sterile barrier between the implant and the non-sterile device. The user can select the correct reactor and insert it in the device. Afterwards, he has selected the implant with the sterilized transfer tool and the sterile implant. You can put it on the device. I think I should be switched on. And then you just put it into the reactor, and the activation will start. So the activation takes 20 seconds, and the implant temperature can rise up to, for instance, 50 degrees. This depends a little bit of the implant geometry. Afterwards, there is the cool down phase, where we suck a lot of air through this reactor, cool the implant down to below 39 degrees. Then the implant can easily be ejected, and the implant procedure can follow as usual. Okay, so I really would like to hear your feedback to this procedure. Maybe you can write us directly or via email afterwards. What we think this device delivers is a chair-side plasma activation to nearly all implant systems. Due to our transfer tool, we are independent of the implant systems if there is an insertion post or not. The overall activation takes less than a minute, so it depends a little bit. We're now testing and optimizing but it should be 40 seconds for the overall process. So what we know so far, this plasma activation is very effective, as we have shown already in the in vitro studies, and also in vivo studies are commissioned. And so far we know from the examinations at the high school in Osnabrück, this is very reproducible, and still the activation is very homogeneous over the implant. Due to the circular plasma exchange around the implant without having to turn the implant or having to turn the plasma source. Even this device will be developed to solve all safety constraints. Okay. Then I will just demonstrate some further use cases, which we have seen from the colleagues today in the morning from Dr. Schweiger and others which are already using our plasma devices in their daily work. On the right, you see images of plasma application with the Piezo on titanium implants or on zirconia implants with the open nozzle. And on the bottom, you see two videos from Dr. Reichermeier, who is using the Piezo brush already in his daily work on implants. You see as a test liquid, so here it's a test liquid that is platelets, patient's own platelets plasma, so medicine plasma liquid, and they use it to enhance the osseointegration, and therefore they want to have this liquid homogeneously distributed about the implant. But what happens when they unpack the implants, you will see in the left video. So if they want to apply the liquid to the implant, you see it appears somehow hydrophobic. So the liquid is totally pushed away, and no droplets form on the implant. Then they do the plasma activation with our device, and you can recognize a nice wettability of the implant, and therefore they know that this liquid interacts with the implant, and they have better results in the patient. Okay, so what we have seen from colleagues today was the dental lab and also the usage at the patient at the doctor, where we have crowns, abutments, ceramics, which are glued, which are painted and need a better adhesion, which should be really, really clean, so super fine cleaned, or also very good in the wettability. So we would really be happy to know more of your ideas and experiences with our plasma devices. So I'm now over with my presentation, and I'm open for questions.
Where can the infrared constant be bought?
Okay, as the name already tells, the device is currently in development and cannot be bought so far. We're searching for a strong partner which can register it as a medical device, and we are just getting developing currently. So far, if you want to activate your implants, you can use this approach.
And can this infrared constant be used for all types of implants?
Okay, so far it can only be used for metallic implants, as there are some specific problems appearing from safety with non-conducting implants. We have already technical solutions, but as the market today is more focused on titanium implants, we are also focusing on this market first.
Is the surface of the implant touched by the plasma?
Okay, no. So the plasma effect is not working on a microscopic scale on the surface. We did a lot of technical research on the surfaces, which we know are very, very sophisticated, provided by the manufacturer. So we did a lot of measurements with electron scanning microscope, with atomic force microscopy and XPS measurements to demonstrate that the surface specified by the manufacturer is not destroyed, touched, or changed.
That's it for the moment.
Okay, thank you very much. And I will hand over to my colleague Simona Derlach again.
Hello again, and now we are coming to a Q&A session. So if you have questions and to be answered or you are sure about relation, so please answer now. Maybe from our side, if you are interested in this technology, if you want to use it, you can rent our device for a small fee on site in your laboratory, chairside by the dentist. And you can choose different knuckle types for the different applications we have presented to you today. And maybe you found new fields of application we do not really know now, but we want to know from you. Exactly. So the other side is that we are looking for strong partner in development for our implant wrap system. And also we are looking for partners selling our products. So if you're interested to say it's a good product, I want to have it in my product range, please contact me. I'm very open for every discussion. So do we have further questions?
No.
So thank you very much for your kind attention to our webinar today. We have a third webinar in planning for end of July, 29th of July. We would be very happy if you would come back and attend as a participant to our webinar. And if you have a great idea and you say, it's great, I have tested your devices, so be a reference from us. Thank you very much and have a nice day.